Okay, so now that we've shown that the statement is true for the base case, let's actually do the inductive step. So the first thing we're going to do is we're going to assume that it's true for n. So in other words, we're actually going to state the inductive hypothesis. So the inductive hypothesis in this case is going to be, we assume PMW for every string in sigma star. And so of course here this sigma is the same input alphabet as the machine M, right? Because we're trying to prove the correctness of this machine M. And so we're assuming PM of W is true for every string W in sigma star, where the length of W is equal to N. And now in the inductive step, what we want to show that for every string W in sigma star, where the length of W is n plus 1, P of MW is true. So that's what we want to show. So how are we actually going to do this proof? Well, let's start by let's pick some arbitrary string W in sigma star, which has length n plus 1. So of course, needless to say that n is in the set of natural numbers. Okay, so we have some arbitrary string W in sigma star, which has length n plus 1. Now we're going to show that the statement PM of W holds. Okay. And so to do that, we're going to use a trick, which is going to come up several times again in the future. And that's going to be to break up the string into two components. So because we know that the length of the string is n plus 1, we know that it has length at least 1. Then perhaps it has some additional symbols in it, n. And so that means that W can be written as x sigma, where x is some string in sigma star, where the length of x is n, and sigma is some letter of the alphabet. And so of course, the length of a string with a single symbol is 1. And so this works out, the length of W still remains n plus 1. So we have this arbitrary string W, and now what we need to show that for this W, P of 1 implies Q of 1, and P of 2 implies Q of 2, and P of 3 implies Q of 3. And so I'm only going to do in this video this proof, but I encourage you to do these other two, and I'll post a notes so you can check whether your work is right. Okay, so let's actually do this first one. So here we're going to show if P1, then Q1. And so I think it'll be easier for you to follow if I rewrite it. So what is this actually saying? It's saying that if delta star Q0W is Q0, then my string W must look like ABN for some n integer greater or equal to 0. Okay, so this is the statement we're trying to show. Now, because this is an if-then, I'm going to do a direct proof. And I'm going to assume the hypothesis and try to show the conclusion. So let's assume P1 is true. So in other words, I'm assuming this is true. Right? So I'm assuming that for this arbitrary string W, I started at Q0 and I ended in Q0. And my goal is that I want to show that W actually looks like ABN for some n greater or equal to 0. Okay, so the first thing I'm going to do is I'm going to rewrite W as what I said it looked like here. So I'm going to rewrite W as X sigma. And now what I'm going to do is I'm going to apply the definition of the extended transition function, and in particular, I'm going to apply the recursive case. And so the reason for this trick is because it works very well with the recursive case of the extended transition function. So that's why I didn't pick sigma x, right? I picked x sigma because that looks like the recursive case for delta star. And so what is this equal to? It's equal to delta star Q0x sigma equal Q0. Right, okay, so these are a bunch of symbols. What is this actually saying? So remember, delta star is this generalized operator that says, give me some state and then some string, and then I'll tell you where you end up in. And so in this case, the string was x sigma, and in this case, you ended back in Q0. But you can also write this as, say you start in Q0, you read some string x, then you end up in some intermediate state p, and then from that intermediate state p, you read sigma. Okay, so you either read the whole string directly, or you read it piece by piece. So you read it first as x, and then as sigma. And so what that means is that this is actually a state. So this is a state, right? And this is a symbol. And so what we're going to do now is we're going to analyze our machine M, and we're going to see actually that there's only one possibility for the state and one possibility for the symbol. So to do that, I need to magically make M appear. There you go. There's M. So now, let's analyze this a bit. I know that I have to be in some state, and I have to be reading some symbol and going back to Q0. So now if I look at my machine M, what state can I be in where when I read a B, I go back to Q0? So clearly it can't be Q2, right? Q2 is some garbage state. That's just some black hole where it just stays at Q2, whatever it reads, whatever M reads. It can't be Q0 because when Q0 reads B, it goes to Q2, but it can be Q1. If it's Q1 and it reads this B, then it goes to Q0. And it can't be any of the other states and symbols, right? Q0 when it reads an A, then that goes to Q1, that's no good. Q1 when that reads an A, that goes to Q2. So it seems like the only thing that's going to satisfy this, this equation is when that state is Q1 and that symbol is B. Okay. And so that's simply by construction of W, right? And so by construction of, sorry, not of W, of M, by construction of M, delta star Q0x, that has to be this state, right? Remember, this is a state. This state has to be Q1, and the symbol has to be B. Okay. So what's nice now is that I actually can use my inductive hypothesis. Right? I can use my inductive hypothesis because my inductive hypothesis states that Pm of W is true for any string where that string has length n. So remember, Pm of W is a conjunction of implications. Okay? And it's a conjunction of implications where in this case I have this statement being true. Now this is actually part of the statement if P2 then Q2, right? So now let me just recall. So recall that in Pm of W, if P2 then Q2, that statement is if delta star Q0W is Q1, then W is ABN A for some n greater or equal to 0. But now recall that this holds in the inductive hypothesis, right? So this statement is true for the inductive hypothesis, right? So this is in the inductive hypothesis. And in particular, the inductive hypothesis says that W must have length n, right? So some string W must have length n. And so in this case, because I have a string x and it has length n, and I have this premise, right? And I know that this is true, right? It's true by the inductive hypothesis. Then I can satisfy the premise of this implication, right? And then I know that my string x is going to look like ABNA. So this implies that x looks like ABNA by the inductive hypothesis. Right, so the only reason I could do this is because I know the inductive hypothesis is true. Because it's true, I know that this implication is true. And so I know that x can satisfy this implication because it has length n. And the inductive hypothesis works on strings of length n. So now I have this result, right? I know that x is ABNA. And I also know that sigma is B. And so then if I put these two things together, remember I assumed that W was X sigma. And so that means that W is ABNA concat B. Or in other words, that means that W is ABN plus 1. And if I just let M be some integer equal to n plus 1, then I have that W looks like ABM, where m is some integer greater or equal to 0. And that shows that Q1 is true, right? Because remember, what I was initially trying to do is I was trying to show that if this statement is true, then my string W looks like ABN for some n greater or equal to 0. And so that's exactly the result I have here. Excellent. So that means that I've shown this statement. And so all that's left to do to finish my proof by induction is to show in the same manner that P2 then Q2 is true and P3 then Q3 is true. And so I'll handwrite this in the notes, but I encourage you to do it first and then to check your work.